Welcome in Darkcore. Astronomers using JWST have spotted 300 unusually bright objects, some possibly galaxies from the universe's earliest era. One is confirmed at a redshift of 8.679, shining just a few hundred million years after the Big Bang. Keep watching this video to see how these discoveries could reshape our understanding of early galaxy formation. The discovery of the James Webb Space Telescope is designed to detect faint light from the most distant part of the cosmos, making it ideal for probing the early universe. In this study, the researchers observed 4 deep sky fields, regions deliberately chosen for their lack of nearby bright objects covering about 500 square arc-minutes. They used 2 of Webb's main instruments, the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI. Because the universe has been expanding for over 13 billion years, light from extremely distant galaxies has been stretched to longer wavelengths in a process called redshift. This shift moves the light from visible wavelengths into the infrared, which JWST is optimized to detect. Higher redshifts correspond to earlier points in cosmic history. To find their targets, the team employed the dropout technique, which looks for sources visible in redder filters but absent in blue ones. This effect is caused by the Lyman break, a sharp cut in a galaxy's spectrum created when neutral hydrogen absorbs ultraviolet light. In very distant galaxies, this cut is shifted into the infrared, making it a useful tool for identifying high redshift candidates. Once potential objects were identified in the imaging data, the team used spectral energy distribution (SED) fitting to estimate their redshifts, stellar masses, and ages. This method compares the observed light across multiple wavelengths to theoretical galaxy models. Of the 137 objects with both near and coverage, about 2/3 appeared to be nearer galaxies with redshifts between 1 and 4. However, at least 7% show signs of being much more distant, possibly dating back to the universe's first few hundred million years. One has already been confirmed at Z at 8,679 through spectroscopy, placing it roughly 570 million years after the Big Bang. Scientific importance and theories, the standout feature of these candidates is their unexpected brightness. According to current galaxy formation models, early galaxies should generally be smaller and fainter, gradually building mass over time through mergers and sustained star formation. These objects appear far more luminous than such models predict for their potential age. If many of these sources are confirmed to be high redshift galaxies, it would imply that galaxy formation in the early universe was faster and more efficient than we currently believe. One explanation could be that they formed in massive dark matter halos that collapsed early, providing deep gravitational wells to draw in large amounts of gas quickly. This could have triggered intense star formation well before models expected. However, there are other possibilities. Some of the candidates may be lower redshift galaxies whose colors mimic those of very distant galaxies. Dusty starburst galaxies rich in gas and dust and forming stars at high rates can appear extremely red in infrared images, as can certain types of active galactic nuclei. Without spectroscopy, it's difficult to distinguish between genuine early galaxies and such lookalikes. The dropout technique is efficient for identifying likely high redshift objects, but it's not definitive. It relies on color-based selection, which can be misleading when dust, unusual star populations, or active black holes affect a galaxy's light. This is why spectroscopic follow-up is essential. It can provide a precise measurement of redshift and reveal the chemical composition and structure of these objects. JWST has repeatedly found bright, distant galaxies that seem more mature than expected, suggesting our models may underestimate star formation, gas cooling, or dark matter halo growth, and hinting at unknown factors in early galaxy formation. Implications and what's next. The next stage for this research is spectroscopic confirmation. While photometric methods like dropout selection and SED fitting are valuable for building candidate lists, spectroscopy is a gold standard for confirming an object's distance and properties. By dispersing a galaxy's light into its component wavelengths, astronomers can identify distinct features such as emission or absorption lines that act as a fingerprint for redshift, chemical composition, and star formation history. JWST's NIRC instrument, along with large ground-based telescopes, will be crucial in this follow-up work. Spectroscopy will reveal whether the brightness of these objects comes from unusually rapid star formation, the presence of active supermassive black holes, or a combination of both. It will also help determine whether dust is playing a significant role in shaping their observed colors. If a substantial number of these 300 candidates are confirmed to be beyond redshift 8, it would pose a serious challenge to existing galaxy formation timelines. Models would need to account for galaxies assembling and producing large numbers of stars much earlier than previously thought. This could lead to revisions in our understanding of gas cooling processes in the early universe, star formation efficiency under primordial conditions, dark matter halo growth rates, and their ability to capture and retain baryonic matter, the role of early galaxies in cosmic reionization when the first luminous sources ionized the neutral hydrogen permeating space. On the other hand, if most of these objects are confirmed to be closer galaxies, the study will still provide important benefits. It will refine the methods used to identify high redshift galaxies, reduce contamination in future surveys, and improve our understanding of dusty starbursts and other lower redshift phenomena. Outro JWST's discovery of 300 bright objects offers a peek at the earliest galaxies or processes that mimic them. One is confirmed from under 600 million years after Big Bang. Confirming more will either reshape early universe models or sharpen our detection methods. Keep watching to see what these cosmic candidates reveal. Thanks for watching Dark Core.